So we're back in Algebra 2 Honors section 4.5, but this is a continuation of what do we do with a polynomial once we find its zeros. So the goal here of all of this that the rest of the chapter has been building up to is we want to be able to graph a polynomial, obviously without a graphing calculator to help us. So we can use our knowledge of factors, we can use our knowledge of synthetic division, we can use our knowledge of end behavior to get a decent sketch of the graph. For example, in the function y equals 2 times quantity x plus 1 times quantity x minus 2 times quantity x minus 3, it's already factored for us, so that's convenient. And I can think about what these main pieces of the polynomial are going to be to answer some questions. So the first one that we have here is the leading term. I don't actually see the leading term outright because this is in factored form, so I have to think about if I were to multiply all this out, what would I get for the leading term? We did actually multiply all of this out in section 4.2, but I don't want to do that whole expansion. I just want to think about what's the first term or the term that would be leading with the highest degree. So I would have this 2, and I would have this x times this x times this x. So this would end up being 2x cubed plus yada yada. We don't know what else there would be. We don't care about those middle terms for right now. So the leading term is 2x cubed. That tells me some things about the end behavior. Because the leading coefficient is positive, I know that as x approaches positive infinity, which is going to the right, y would be going up towards positive infinity. I also know as x approaches negative infinity, which would be the left end behavior, y approaches negative infinity, because the degree is odd, so the end behaviors are different. I'm going to just mark this on my graph by putting a little up arrow and down arrow so that I remember that that's what's about to happen here. I can also find the zeros then of this polynomial because it's given to me in factored form. If I set this equal to 0, if I set y equal to 0, I can see that I would end up with x equals -1, +2, and +3. So that's where the graph is going to cross the x-axis. -1, +2, and +3. So I can put those on there. For the y-intercept, I would want the constant term, so I can either think about what that expansion would be, or I can go ahead and put in 0 for x. So if I put in 0 for x, I would have y equals 2 times 1 times -2 times -3, which would be y equals 12. So I know that my y-intercept would be up here at 0, 12. And then from that, we can kind of just piece in the graph. So just using some good guesses, I know it's got to be up to the right. So look at that. If I swoop through all those zeros and I go to the y-intercept of 0, 12, more or less, that's going to give me an okay sketch of what that polynomial looks like, which is pretty amazing that we can do that without any calculator at all. Now, I don't actually know that the maximum point here is at 0, 12. It could be quite possible that that is not our maximum, in which case I could have something that looks like this. Maybe it goes higher than 0, 12 and then just kind of hits it back on the way down. I don't really know, and that's not what we're concerned about right here. We're just trying to get a sketch, which means all the important features, the x-intercept, the y-intercept, the end behavior, the shape of the graph. If we look at this function, though, we're going to run into some problems here. The leading term of this function, if I multiplied it out, would just be x cubed something, something, something. So the leading term is x cubed, means that this function's end behavior is going to be the same as the last, that as x approaches positive infinity, this would go up, and as x approaches negative infinity, it would go down. But if I look at the zeros, by setting the function equal to 0, I get x would equal -3 or +1. So I can go ahead and put those on the graph, that the zeros would be at -3 and +1. This fact, the second factor, which is x plus 3, is the same as I already had, so I can put a second dot at x plus 3, but it's the same dot, so it doesn't do me any good. And so I only have 2 zeros in this case. I can also find the y-intercept. If I put in 0 for x, I would have 3 times 3 times -1. So the y-intercept would be down here at -9. So if I try what I did on the last problem, and I know that it starts up to the right, and it has to go through that, and has to hit that y-intercept, and then goes through that one, I end up not getting what I need because it ends up going up on both sides, and I know that it's got to go down to the left. So something has to be off here, and that's where we can use multiplicity. Multiplicity means how many times is that 0 a 0? Or how many times does that zero's factor appear in the polynomial? So in this case, I could write this polynomial as x plus 3 quantity squared times x minus 1. So the fact that there are 2 copies of the x plus 3 factor means that that factor would have even multiplicity, whereas the x minus 1 factor is to the first power, and so that would be odd multiplicity. Turns out any even multiplicity will give a turn 0, where the graph will not cross the x-axis, but will turn back from whence it came. If there is odd multiplicity, then that will be a cross or a cut 0, where it cuts through the x-axis or it crosses that gate, right? Crosses the gate of the x-axis. So in this case, if I redo this graph to think about multiplicity, x minus 1, that factor has multiplicity 1, which means this 0 would have to be a cross or a cut 0. So I can start by saying, all right, I know it's got to cut through there, and it has to hit the 0, -9, and it has to get back to this 0. But when I get to the 0 at x equals -3, I would make that note to myself that the multiplicity here is even, which means this is not going to cross the x-axis, but merely touch the points and then turn back. And actually that helps me out because now I'm going up to the right and I'm going down to the left, so I've satisfied the end behavior that I knew needed to exist. I also have all of the zeros that I need and the and the y-intercepts that I need, and so that multiplicity really helps me out. Alternatively to multiplicity, you can always check by making an xy table and putting in values for x in each piece. In other words, between all of the zeros, we could put in a value to check. So if I put in -2, I could either check that using synthetic division. If I had this, I'll expand it out, or I can just put it into the factors, and I would get 1 times 1 times -3. So I know that this can go through -2, -3. And then if I pick a point to the right of x equals 1, so I pick f of +2 perhaps, then I would get 5 times 5 times 1. So I would go through the point 225, which would be, way up there. So that can kind of tell me, and then I could do one on the other side of x equals -3 as well. So I could do potentially f of -4, and that would give me -1 times -1 times -5, which is -5 for f of -4. So I can do that, and that would give me clues as to where the direction of this polynomial is turning. But multiplicity ends up being way more efficient and also will help you out in pre-calculus. So I have 2 examples of this that we're going to finish with, and we're going to see if we can get both of these sketched. One of them has a little bit more work than the other one, but you should have a pretty concrete idea of how to graph a polynomial after this. So the first one is given in factored form. to find the degree and the end behavior, I'm going to have to think about what the leading term would be. So if I multiplied all of this out, I would have negative 2x times x for that leading term, and that would be negative 2x cubed. That tells me that this is a third degree, so as x approaches negative infinity and as x approaches positive infinity, those are going to be different end behaviors. The leading coefficient is negative 2, so I know that as x approaches positive infinity, y is going to approach negative infinity, which means on the other side, it would approach positive infinity. I'm going to draw myself little arrows here just so I don't forget that I'm going to go up to the left and down to the right. Okay, so then let's look at what the zeros would be. If I set each factor equal to 0, I would get for my zeros x equals 0, 1, and negative 5. So I'm going to go ahead and plot those on my x-axis, 0, 1, and negative 5. For the y-intercept, well, I can see that that's 0, 0 because it can only cross the y-axis once in order to be a function, and I already have a y-intercept down, so I'm not going to worry anymore with that. Each of these zeros has a multiplicity of 1, which means that they all are just going to cross the axis and just cut through that axis. So if I start on the left side this time, just to mix it up a little bit, I know I'm going to go through there, through there, through there. And look at that, I was able to get through all of the zeros and my end behavior correctly, and there's that polynomial sketched. Remember that all polynomials are smooth curves, so you shouldn't be changing concavity. For instance, we wouldn't just decide randomly to make it turn funky ways, because then it wouldn't be a nice smooth polynomial. Smooth is actually going to be something that's pretty important when you get to calculus. So just make sure that it's a nice smooth polynomial, but we don't know exactly how low that goes or how high that goes there, so don't worry about that. That's why I don't have any tick marks on my y-axis. All right, last example. Y equals 2x to the fourth minus 5x cubed minus 13x squared plus 15x plus 21. That looks pretty extensive there, and as I look at that, that's 5 terms, so I don't have a method that will factor anything with 5 terms for me. So I'm going to have to use some of the material from the beginning of the section to maybe potentially look at my possible rational roots and see if there's anything that I could divide out there. Let's start by looking at the degree. The degree would be 4, which means the end behaviors are going to be the same. And the leading coefficient is a positive 2. So as x tends toward negative infinity, y would go up toward positive infinity. And as x approaches positive infinity, y would also approach positive infinity. That would be up to the right and up to the left. The zeros, I don't know, I'm going to have to do some work on that. The y-intercept would be 0, 21, so we can go ahead and put that on our sketch. And now let's go ahead and find our zeros. So we're going to look for possible rational roots. I'm just going to erase this other question that I had over here. So we're going to look at possible rational roots and then see if we can find one to divide out. And I'm going to take my factors of 21 over my factors of 2. So my possible rational roots would be x equals plus minus 1, 3, 7, 21 over 1 and 2. If I list all those out, that would be, I'll go ahead and list them separately. 1, 3, 7, 21, 1 half, 3 halves, 7 halves, 21 halves, and then the negative of all of those as well. So negative 1, negative 3, negative 7, negative 21, negative 1 half, negative 3 halves, negative 7 halves, negative 21 halves. You can see we've got 16 choices for possible rational roots. This is where on the instructions it said, well, if you use a graphing calculator to help you, or perhaps I would give a hint to you on the test so that you're not wasting a bunch of time, we can look for an x-intercept so that we make a smart decision on what we would like to quote-unquote guess for a rational root. And so in this case, I'm just going to guess, I'm just feeling like x equals -1 is gonna be a good bet. I'm gonna see if that works. So I'm gonna put my coefficients to -5, -13, 15, 21, and I'm just gonna try x equals -1. So I'm gonna drop down the 2, multiply and add. What do you know, today must be my lucky day because I got a remainder of 0. So x equals -1 works. That means I know it goes through -1, 0. And what I have left then is a cubic, so this would be 2x cubed minus 7x squared minus 6x plus 21. And so now I'm back to the beginning where I say, well, can I factor this? It's 4 terms, and it does look like that it potentially is going to factor by grouping, so let's give that a shot. The first 2 terms have x squared in common with 2x minus 7 left over. And the second 2 terms have -3 in common with 2x minus 7 left over. So that means that the polynomial that I had left after I divided out this 0 of x equals -1 ends up being x squared minus 3 times 2x minus 7. That's not the original function, but that's what I have left after I've taken out one of those zeros. Well, that helps me because now I can set that equal to 0 to find the remaining zeros. If I do that, I would get either x squared minus 3 equals 0, or 2x minus 7 equals 0. If x squared minus 3 equals 0, that's a quadratic that I can solve by taking square roots since there's no b term. So I'm going to get the x squared by itself and then take a plus minus square root, and I get x equals plus minus root 3. That makes sense because every irrational 0 had to come with its conjugate pair, and those are conjugate pairs of each other. If 2x minus 7 equals 0, then I would get x equals 7 over 2. So let's go ahead and put those on the graph. X equals 7/2 is 3.5. And then the square root of 3 is approximately 1.732. So positive 1.732 and also then negative 1.732 approximately. So I've got 4 roots on that graph. We can make sure that those were on our list. Well, -1 was on the list. I already have that one circled. And 7/2 was on our list. But this plus minus root 3, neither one of those was on our list. But you can remind yourself that those are irrational. So our list is only the rational choices and doesn't list the possible irrational choices, of which we have no list for. So if I write out the factorization, the linear factorization of this polynomial, I'll call it f of x up here, then this would equal, if I take my equal sign from right to left, this would actually equal x plus 1, which was the first 0 that I divided out, and then I'd have the x squared minus 3 and the 2x minus 7. If I produce from that the linear factorization, that would be x plus 1 times x minus the square root of 3 times x plus the square root of 3 times 2x minus 7. Generally, we don't actually like producing a linear factorization if those are irrational numbers. But that helps us because it helps us with the multiplicity, that I can see that all of these have a multiplicity of 1, which means that those are all cut through the x-axis zeros, which means I'm going to just draw a nice smooth curve that's going to go through all 4 of those. And since the zeros are not the same distance apart, most likely that those minimums would not actually occur at the same spot. And we don't know that our y-intercept is actually a maximum or a minimum either, so I don't want to make it look to you like it's going to be beautiful and symmetric. It's probably not. But there we go. So now I've gone through all 4 of the zeros and the correct y-intercept, and I have the correct end behavior. That was definitely more work than the first function, which means that you should feel even more of a sense of satisfaction at your command of graphing polynomials. So well done on section 4.5.